This section is section 4.4. We're going to take a look at solving more equations. Some of the versions of this are types of equations we've seen before, and some of them are new. The basic idea when we're solving logarithmic equations, however, is to consolidate things to one log, or one log on both sides of the equation, and then be able to solve from there. So let's take a look at some examples of that. The first two examples have that already. We have one log, and it, in this case, is on one side of the equation. Now, the first one and the second one are ones that we've seen variations of this in our last section. So remember, this is log base 10, and we draw our circle around and rewrite. So this would be 10 to the power 1 equals x minus 6, or 10 equals x minus 6. If we add our 6, we get that x is equal to 16. Now, we talked about last time that there are certain values, namely negatives, that we have to be careful about not showing up inside of a log. So we want to make sure that no matter what answer we get, we look back at the original expression and make sure that it doesn't give us a negative inside of our log. On this one, there's an x minus 6, so if I put 16 in there, 16 minus 6 would be 10, and we're good to go. All right, our next one looks a little bit different. We saw, again, a problem like this kind of happened last time where the base itself was what we're trying to find, the variable. So again, we're going to circle to rewrite the same way we've done on the other ones. This actually gives me x to the 1/4 equals 16. Now, we talked about this last time. 1/4 would be the same thing as a fourth root, so if you like that, you can certainly write this as a fourth root of x to the 16th. Either way, the way that we would counteract or invert or undo a 1/4 power would be to raise things to a power 4. So if we raise things to a power 4 on both sides, and again, it might be easier for you to see it in radical form, right? A fourth root's opposite would be a power of 4, right? So it's the same thing, of course. And if you grab your calculator, you will very quickly find out that 16 to the 4th is actually 65,536. All right, the next one looks considerably more difficult, and it is. There's a lot more going on with this particular problem. The first thing you should notice that there's something going on is that there are two log expressions, log base 2 of a minus 2 over 5 and log base 2 of a plus 3 over 10. You might also notice that there's a 0 on the other side of the equation, also unique. Haven't seen that one yet. And the insides of our logs are actually fractions as well, which makes it a little bit messy. Now, the first thing we'd like to do, like I mentioned at the beginning of this section, is that if we have more than one log, we want to somehow consolidate, get it to become one. So in particular, these logs are added together, which means that the interior of the logs need to be multiplied. So this is log base 2 of a minus 2 over 5 times a plus 3 over 10. And all of that equals 0. Now, we'll clean up the inside just a little bit, write out what it actually is, and then we'll deal with changing this into an exponential like we've been doing in the last problems. Clearly in the numerator I've got a squared, and then I have minus 2a and plus 3a, which would be plus an a, and then minus 6. In the denominator we have the very interesting number 50, a little bit larger than we normally deal with, but that's okay, and equals 0. Okay, so now it's in at least the form where I have one log on one side, and I can rewrite. So I circle my 2 and draw the arrow around. So this would be 2 to the 0 equals, and it's all the same expression as before, a squared plus a minus 6 over 50. Now clearly 2 to the 0 is 1, and then we can multiply that by the 50 that's in our denominator, right? So I have a squared plus a minus 6. And this is 50 on the left. Okay. And then we'll come up here next. We can actually move it onto the same side. So if I move the 50 over, I've got a squared plus a. Let's see, and minus 6 and minus 50, so minus 56. And this is equal to 0. All right, thankfully for us, this does in fact factor. So we are going to factor this guy, obviously a and a. And I need two numbers that multiply to give me 56 and add to give me a positive 1 in the middle. So a positive 8 and a minus 7 would do that, I believe. And if we follow this through, we now have a is equal, sorry about that, to negative 8, and a is equal to 7. There's a 0 over here. Okay, so looking back, again, we talked about this, right? Looking back at the original problem, we want to make sure that neither of these answers actually makes the interior negative. And in particular, the negative 8 does. On the first one, negative 8 minus 2 would give me a negative 10 over 5, or negative 2 inside of this log, so that's a problem. If you take a look at the 7, it doesn't pose that same problem. I have 7 minus 2, which is 5, divided by 5 is 1. And I've got 7 plus 3, which is 10, divided by 10 is 1. So we actually get 2 solutions on this one. All right, let's move on to another one. This one starts out feeling much like the last one, where I have 2 individual logs. I do have a subtraction sign on this one, which means we're using division. So I have log base 4, and again the division would put x on the top and x plus 2 on the bottom of the interior of the log, and this equals to 2. Now we're going to rewrite it again as an exponential. Seems to be the name of the game today, right? So I have 4 squared, not 4 squared like the game, but 4 squared equals x over x plus 2. Okay, so clearly 4 squared is 16, and I can multiply by the x plus 2 on both sides. And so now I have 16x plus 32 equals x. If I subtract my x and subtract the 32, I have 15x equals negative 32, which divides by 15. Now, that might not look like a problem to you at the get-go, right? But we want to make sure that it works inside of the original equations. And in particular, this is already a negative value, and so I can't use it because the inside here, right? Oops, that's not a good color. Let me try a different one. The inside here is just x, so anything negative is not going to work. So this one doesn't work. So what do we have to do? Well, if that's the only possibility and it doesn't work, then that would mean that you have no solution. All right, this one sort of feels like it's different because the logs are on the different sides of the equation. But again, the goal is to get the logs together and consolidated. So we're going to move the log of x minus 1 over to the left. So I've got log of 4 minus log of x minus 1 equals 1. Now I can consolidate each of these. This is log, and it's 4 over x minus 1. Remember, it's subtraction because it's subtraction, we're using division. All right, and this equals 1. All right, and we're going to start then with the base. And of course, we all know that the base is understood to be a 10 in this scenario. So I have 10 to the 0, or I'm sorry, 10 to the 1, excuse me, equals 4 over x minus 1. And we'll multiply, or cross-multiply if you prefer to think it that way, each of the numbers. 10 to the 1 is just 10, right? And we're going to multiply by x minus 1, and that equals 4. This is 10x minus 10 equals 4. We can add our 10 to the other side. Yeah, that's definitely a good plan. And then I have 10x equals 14. And divide by 10, we actually get that x equals 14 over 10. And then that will reduce to 7 over 5. And again, we should check to make sure that it really works. If I'm putting a 7 over 5 in there makes any problems. 7 over 5 is slightly bigger than 1, so the x minus 1 should be good. That's the only variable in the problem. All right, this is our last example for today. Again, you'll notice that there's a log base 3 on both sides, so we can combine them. Because this is addition, we're going to combine them with multiplication. And an interesting thing is going to happen. In particular, we have x times 1 over x. And log base 3 then, that would be of 1 equals 0. But we talked about last time the fact that this right here is always equal to 0. So the log base 3 of 3 is 0, which makes this correct. So what does that mean? I mean, like, we're supposed to be answering the question of what is the correct solution, and we kind of got this fact that 0 equals 0. What does that mean? Well, it means that all of the x's will work if they're in the domain. So this actual answer is all x greater than 0, because we know we can't have inputs that are actually less than that.